Okay, we're going to finish up 6.1 here. Here's the thing about these confidence intervals. The population mean is a fixed value. So even if we don't know what it is, which lots of times we don't, it exists in the world and it's fixed at some value mu. And then what we're doing is we're figuring out a confidence interval around a point estimate of sample mean. So let's just say I'm going to draw several different confidence intervals because, as you know, I could take one sample. Let's say this sample has a sample mean that's slightly above mu, and my confidence interval goes from here to here. Well, this particular sample happens to capture my mean. So let's say I have another sample and it's over here and I'm going to have the same size of confidence interval and it also captures mu. Then I have another one up here and it barely captures mu, but it's still in there. And so I have all these different samples that I can create, pretend that's the same size, and they're almost all going to capture the actual population mean. Maybe one of them is like right on the population mean. So what ends up happening is that in the long run, if we have a 90% confidence interval, then how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, so I need 10 of them. For a 90% confidence interval, what happens is 9 out of 10 of my intervals actually include the mean. So that's the meaning of it. For a 90% confidence interval, 9 out of 10 samples in the long run, I may have to do like millions of them, but generally speaking, 9 out of every 10 samples will actually contain mu. So think about if I had an 80% confidence interval, only 8 out of 10 would capture mu. If I have a 95% confidence interval, 95 out of 100 of my little intervals would capture mu based on the same sample size. Based on samples of the same size. So if I have a 99% confidence interval and I took 99 or 100 different samples, 99 of them would somehow contain the mean, and then 1 would be far off enough that the interval would not actually capture the mean. Okay, so that's the meaning of the confidence interval. Now let's look about how to construct a confidence interval. These are going to be like our step-by-step instructions. So we are going to construct a confidence interval for mu, which is population mean, when sigma is known. Okay. Step 1, you have to verify 3 things. 1, sigma is known. 2, the sample is random. And 3, either the population has to be normally distributed, or, what's the other thing it could be? If the population is not normally distributed, then the sample size has to be greater than or equal to 30. Step 2, you're going to find X bar. X bar, remember, is the sample mean. 3, find the critical value. Remember, the critical value is Z sub C. That corresponds to the level of confidence. Okay, just as a refresher, that's going to involve a normal curve. And we're going to have some confidence interval that goes between z sub c and negative z sub c. And what's in between these two is an area of C, where C is our confidence amount. So if it's 90%, then this area would be 0.9000. Then remember that each of these tails has an area of 1 minus C divided by 2. So we look up the area of 1 minus C divided by 2, and that's going to give us our negative critical value. And then we just got to remember to use the positive critical value when we figure out our margin of error. Margin of error. Margin of error is capital E, and it's z sub c, which was our critical value, times sigma, which we're given in the problem, divided by square root of n, which is the sample size. Then you're going to construct the interval by taking the point estimate minus the margin of error, and mu is going to be between that value and the point estimate plus the margin of error. And we are going to round this to the same number of decimals as the sample mean, which is x bar. Okay, let's go back to our grocery store example and construct a different confidence interval just so we get a little bit of practice. So we are going to construct a 98% confidence interval for that grocery store data that we had. So our steps are that we have to verify that sigma is known, and that was given to us in the problem. The sample is random. I believe it stated way back when that they were randomly selecting 30, and that the population is either normally distributed or n is greater than or equal to 30. Since our sample size is 30, we're good. Remember, we had already found our mean, x bar. It was 28.9. We were given sigma was 7.9, and our sample size is 30. So our step 2 was to find sample mean. Step 3, we have to find the critical values. So when we're looking for those critical values, remember we've got z sub c, negative z sub c. Our confidence interval is 98%, so we're going to have 0.9800 in the middle here, which means that each of these sides is going to have 1 minus 0.9800 divided by 2. If you do that subtraction and then divide, that actually comes out to be 0.0100. So you look up 0.0100 as the area on table 4, and that gives you a critical value of 2.33. Step 4 was then find the margin of error. So we need to find E, which was z sub c times sigma divided by square root of n. So we take z sub c times sigma, which was 7.9, divide by the square root of n, which was 30. And then we're going to round to the same number of decimal places as our mean, so only one decimal place. That gives us a margin of error of 3.4. The last thing we do is construct our interval, and we do that by taking our point estimate, which was x bar, so 28.9, minus our margin of error, 3.4. And the mean is going to be between that value and 28.9 plus 3.4. So our mean is going to be in between 25.5, and 32.3. Now, doing all those steps is really great, but we also need to be able to put that in words as to what it means. So what this actually means is that we are 98% confident that the true population mean is between our 25.5 and 32.3 hours. Oh, remember that before we had a 95% interval. So thinking back to our other problem, recall the 95% interval. So if you flip back to your other page, the 95% interval was from 26.1 to 31.7. So let's think about, we are more confident about this interval than we are about this interval. Notice what happened to the width of our interval. When we're more confident, our interval gets bigger. When we're less confident, our interval gets narrower. That's an important thing to pay attention to. So we want to make a note of that. As confidence level increases, the interval gets wider. So we can be more and more confident, but the more confident we are, the wider our interval. So it's kind of like less impressive to be that confident that you can hit a large target. Let's see what happens if we change our sample size. So back to our grocery store example. What would happen if the sample size was 50, and we're going to assume we had the same sample mean. And we're going to construct a 98% confidence interval. So let's see what happens if we change the sample size. What happens to our interval? So we're going to keep the same information. X bar was 28.9, sigma was 7.9, but now our sample size is going to be 50. Since we have the same 98% confidence interval, our critical value stays the same at 2.33. So let's figure out our margin of error, which is z sub c times sigma divided by square root of n. So 2.33 times sigma, 7.9, divided by square root of n, which was 50. And that's going to give us 2.6. So then to construct our interval, remember we take our sample mean minus our margin of error, so 28.9 minus 2.6, and the mean will be between that value and our sample mean plus our margin of error. So mu is between 26.3 and 31.5. Now let's compare that to the other 98% confidence interval up here. So when our sample was 30, our 98% confidence interval was 25.5 to 32.3. But when our sample is 50, our interval is 26.3 to 31.5. So what happens is, as the sample size increases, what happens to our interval? The interval gets narrower. So the higher our sample size, the more specific our confidence interval is going to be, which is a good thing. The narrower your confidence interval is, the more, the less wiggle room you have in saying where the mean is, so the better approximation you have. So what's the right sample size that's going to give us a confidence level? Because what you just saw is, if I have a larger sample size, I can have a smaller margin of error, and if I have a larger confidence level, my interval gets wider. So there's like this balancing point, and we can actually figure that out. So what we can do is determine the sample size that will give us a desired level of confidence. So we get to decide how confident we want to be, and margin of error. So there's actually a formula for that. I'm going to write a little bit up here, so I'm leaving a little bit of space. I'm going to write the formula. It's n equals z sub c times sigma divided by e squared. Now that's just rearranging the e formula. So you don't have to actually write down an extra formula. You can use the original formula. I'll show you that. If we started with e equals z sub c times sigma over square root of n, and then you multiply both sides by square root of n, so now I have e times square root of n equals z sub c times sigma. And then, since I'm solving for n, divide by e, so square root of n equals z sub c times sigma, divide by e. And then to get n without the square root, square both sides, I get z sub c times sigma over e squared. So that's the reason that formula works. You can put that little formula on your cheat sheet, or you can just use the same margin of error formula. But this is how we find the minimum sample size to estimate mu given a C confidence level. That's this, Z sub C, given a C confidence level, and margin of error E. Okay, so what if you don't know what sigma is for your population? If sigma is not known, you can estimate it using S, which was the sample standard deviation, as long as the sample is at least 30. There's that magic number again. Okay, so let's go back to the grocery store example. Back to the grocery store. Suppose the regional manager wants to estimate the mean number of hours worked by all employees in the chain. So what the manager is estimating is mu. So that's mu. How many need to be in the sample? So he or she can be 95% confident. So they're deciding the confidence level, the manager is. And we want the sample mean to be within, we're going to do two problems. So A, if he wants to be 95% confident that the sample mean is within 2 hours of the actual mean, and then we're going to do, if we want the sample mean to be within half an hour or 0.5 hours of mu. So the information that we're using here is that our confidence interval is 95%, and so we can look up the z-score that goes with that is 1.96. What is our confidence level? C is our confidence level, so that is the 95%, so 0.95. Sigma for the problem was 7.9. And we want our margin of error. In this case, margin of error is 2. In this case, margin of error is 0.5. That's how much I'm allowed to be off. I'm allowed to be within 2 hours here, and on this one, within 0.5. So we're going to use our handy-dandy formula that n is z sub c times sigma divided by e squared. So n would be 1.96 times 7.9, in this case divided by 2, and then the whole thing is squared. So you put that in your calculator, multiply those two numbers, divide by 2, square the whole entire thing, and we get 59.938564. So we're going to actually need to round that up, and we're going to have to ask 60 people, because 59.93 is the minimum number of people I'd have to ask. Now let's see what happens if I want to be within half an hour of the actual mean. Then n would be, z sub c is the same, 1.96. Sigma is the same, 7.9. What's different is my margin of error. Instead of 2, like it was there, it's going to be 0.5, and then I square it. So I take 1.96 times 7.9, divide by 0.5, and then square that answer. And we get 959.017024. That's the minimum number of people that I would have to ask. So since it's more than 959 at minimum, I have to still round that up, and I have to ask 960 people.